We've definitely heard of gravity. It is the force that keeps stars dancing in the cosmos, forges mysterious black holes, and yes, makes apples fall, sometimes right onto someone's head. But here's the big question: have we ever really stopped to think about what truly is gravity? Despite being one of the most universal forces in the cosmos, gravity is a bit of an oddball when compared to the other fundamental forces. Unlike the strong nuclear force, weak nuclear force, and electromagnetic force, gravity is incredibly weak. Plus, it only works in one direction: it pulls things together. There's no such thing as anti-gravity that pushes objects apart. When we look at gravity through the lens of quantum mechanics, things get even weirder. Scientists are often stumped by gravity because cracking its code is key to understanding the universe itself. If we can figure out the most fundamental ways the cosmos operates, we can predict how it will evolve. This is why physicists dream of a grand unified theory that ties everything together, but gravity's quirks keep throwing a wrench in that plan. Gravity plays a huge role in our everyday lives. Think about it: the reason we can walk on Earth without floating into space is thanks to gravity. Without it, the universe would be a chaotic mess of dust and gas, no stars, no planets, and certainly no life. But here's the kicker: while gravity feels ever-present, it's shockingly weak. It's about 1/10 to the power of 36 of the strength of the other three fundamental forces. That's a mind-blowingly tiny number. Here's a fun way to put that into perspective. Grab a small magnet and use it to pick up a nail. At that moment, the magnet's electromagnetic force is strong enough to overpower the entire Earth's gravitational pull on the nail. Crazy, right? It shows just how powerful other forces in nature can be, but it also highlights something truly fascinating about gravity. You see, even though gravity might seem weak compared to forces like electromagnetism, it still has a massive role to play, especially when you zoom out to cosmic scales. On smaller scales, gravity may appear almost negligible when compared to the electromagnetic force that can pull a nail from the Earth. But in the vastness of space, gravity is the dominant force shaping everything we see. It's responsible for the orbits of planets, the formation of stars, the structure of galaxies, and the very existence of black holes. In fact, without gravity, stars and planets wouldn't even exist in their current forms. They'd be a scattered mess of gas and dust. Unlike the strong and weak nuclear forces, which act at microscopic scales and have very limited ranges, or electromagnetism, which can cancel out depending on charges, gravity is always attractive and never cancels. It's a constant pull. And this pull increases as objects get more massive. It's like the more mass an object has, the harder it tugs at the fabric of space and time. And since mass can't be negative, gravity only builds, never diminishes. In a way, this makes gravity the ultimate cosmic glue, holding everything from planets and stars to entire galaxies together. Without gravity, the universe wouldn't have the structure we see today. Planets would float aimlessly, stars wouldn't form, and galaxies would dissolve into the void. So, the next time you think about gravity, remember, it may seem weak on small scales, but on the grand stage of the universe, it's the force that keeps everything connected and in motion. It may not be as flashy as other forces, but without it, the universe as we know it would cease to exist. Physicists believe that this interaction happens when one electron throws some kind of particle at another electron. This particle can transfer momentum, kind of like two electrons tossing a basketball to each other, with the photon acting as the basketball between them. This analogy is helpful because, much like how throwing a basketball transfers energy from one player to another, the photon carries the energy from one electron to another, changing its momentum in the process. This is how electromagnetic forces are transmitted, by the exchange of these tiny, massless particles. In the case of weak interactions, the particles exchanged are W and Z bosons. These bosons are quite different from photons. They are much heavier and can only travel short distances. The weak force is crucial for processes like radioactive decay, where subatomic particles change types, such as when a neutron decays into a proton. These processes can only occur within a very tiny range, which is why the weak force has such a limited influence compared to the electromagnetic force. In strong interactions, the particles exchanged are gluons. Gluons are responsible for holding quarks together inside protons and neutrons. Without them, atomic nuclei would fall apart. Unlike photons or W/Z bosons, gluons interact with each other, creating a complex network that holds particles together in an incredibly strong force. But again, this only works over very short distances, within the confines of atomic nuclei. The standard model of particle physics has been incredibly successful in explaining a wide array of natural phenomena. It's the framework that has allowed scientists to understand how the fundamental forces work at the quantum level. Everything we observe in the lab, from particle collisions to the behavior of atoms, can be explained within this model. It's also been able to predict the existence of particles that we hadn't discovered yet, such as the neutrino or the Higgs boson, the latter of which was confirmed in 2012. The standard model even gives us insight into why the weak and strong forces have short ranges. The force carrier particles, W/Z bosons and gluons, are heavy, and their large mass means they can only interact over small distances. However, despite its successes, there's a major flaw in the standard model: it can't explain gravity. Gravity, the force that keeps planets in orbit and makes objects fall to the ground, is conspicuously absent from the model. While electromagnetism, the weak force, and the strong force all have corresponding particles that mediate them, gravity is different. It doesn't have a corresponding quantum particle. We understand gravity well on large scales, thanks to Einstein's general theory of relativity, but when it comes to explaining gravity at the quantum level, we hit a wall. The absence of gravity in the standard model is a major challenge for physicists and highlights one of the most perplexing mysteries in modern science. How can we unify the understanding of the forces at both the quantum and cosmic scales? There are two reasons for this. The first is that to incorporate gravity into the standard model, we'd need a particle to mediate the force of gravity, which physicists call the graviton. If such a particle existed, it would mean that every particle in your body and every particle on Earth is constantly throwing something to each other to create the force of gravity. But the problem is, no one has ever observed this graviton, so this theory could be completely wrong. The second reason is that we already have a theory that explains gravity perfectly: Einstein's general theory of relativity, proposed in 1915. General relativity is already a very complete theory. It describes gravity in an entirely new way, suggesting that gravity isn't a force between two objects, but rather a result of space itself being distorted. Einstein imagined space not as an abstract, empty concept, but as a kind of soft fluid. Mass or energy bends the space around it, which changes the paths of objects moving through that space. In this theory, gravity isn't a force in the traditional sense. It's a manifestation of how spacetime itself is curved. The simplest way to describe Einstein's theory is: matter tells space how to curve, and space tells matter how to move. Here, there's no force between matter and space. General relativity argues that Earth doesn't orbit the Sun because of some force pulling it along. Rather, Earth orbits because the space around the Sun is curved in such a way that Earth moves along an elliptical path. A common analogy is to think of space as a rubber sheet. When you place the Sun on the sheet, it causes a depression. Then, if you roll a ball across the sheet, it will travel in a curved path because the sheet, representing space, is curved by the Sun. But no force is pulling the ball, it's just following the curved space. Of course, this is a simplified analogy. Realistically, the situation is described with math. In this view, gravity isn't mediated by some particle. It's about how much mass can curve the space around it. Although this idea might seem strange, it has successfully explained gravity on both small scales and cosmic scales, and even helped us understand strange phenomena in space. We'll dive deeper into space and its curvature in future episodes. General relativity is an incredible theory. It predicted the existence of black holes, explained the motion of celestial bodies, and even made GPS possible. But here's the problem: general relativity is a complete theory, and quantum mechanics is also perfect in its own way. But the real challenge is that we just can't combine the two theories into one unified framework. Inside black holes, one is the starting point of the Big Bang. Both of these scenarios are very difficult to study. We can enter a black hole, but once inside, we can't get out. The starting point of the Big Bang is far from us. Scientists often say we have studied the very short moment at the beginning of the Big Bang, but why is humanity so focused on getting as close as possible to the Big Bang's origin? This is because through studying it, we can attempt to unify quantum physics and relativity. Another observable phenomenon is the collision of black holes, two supermassive black holes colliding. This is necessary to detect gravity at the quantum level. Of course, we cannot operate two black holes to make them collide, as we don't have that ability yet. However, due to the vastness of the universe, we can patiently search and discover various phenomena happening in different directions and distances, such as colliding black holes. When two black holes get close, they try to devour each other and spin faster, entering a death spiral. During the merger, gravitons may be emitted in all directions, and our task is to detect these gravitons. However, this is not easy. Even if black hole collisions generate gravitons, their gravitational signals are extremely weak and almost undetectable. Scientists have calculated that even near a strong black hole radiation source, we would need a receiver as large as Jupiter to detect one graviton every 10 years, assuming gravitons exist. After discussing the method of detecting black hole collisions, let's look at another approach: finding a situation or designing an experiment that causes the two theories to give different predictions, using this contradiction to test which theory is correct. For example, exploring the interior of a black hole, general relativity states that there is a singularity inside the black hole, with extremely high density and spacetime curved to its limit, whereas quantum theory does not accept this, believing that matter cannot be as small as a single isolated point. As space becomes smaller, its uncertainty becomes larger. This indicates that one of the theories must be wrong. If we can reveal the true nature of a black hole's interior, we can gain key clues to understanding the interaction between quantum mechanics and gravity. However, the difficulty in realizing this idea is immense. Not to mention whether we can safely return, just entering the black hole could tear us apart. Another related research topic is gravitational waves. When massive black holes merge, they cause ripples in spacetime, just like how water ripples when two speedboats spin. These ripples in spacetime are called gravitational waves. Simply put, moving mass disturbs space, and this disturbance propagates like waves. When gravitational waves pass through, they stretch and twist objects in their path. Circles become ellipses, squares become rectangles. However, this deformation is very difficult to observe because the distortion caused by gravitational waves is tiny, only 1 in 10 to the power of 20 of the object's original size. For example, a stick 1 light-year long would shrink by just 1 millimeter due to gravitational waves. To detect this, scientists have designed a laboratory called LIGO, Laser Interferometer Gravitational Wave Observatory, which uses two perpendicular 4-kilometer-long pipes. It measures tiny changes in the length of the pipes using laser interferometry to detect the presence of gravitational waves. Gravity is different from everything we've encountered in the realm of fundamental forces. While the other forces have clear, quantifiable mechanisms that govern their behavior, gravity seems to act in a much subtler, more universal way. It may not be special in the sense that it's somehow unique, but rather, it's simply a consequence of the way our universe is structured. The vastness and simplicity of gravity's behavior make it a force that transcends the others, influencing everything from the smallest particles to the largest cosmic bodies. Our ultimate goal as scientists is to understand the nature of this universe, and perhaps, part of this understanding involves resisting the urge to assume that gravity should behave in a particular way based on our preconceived notions. Instead, we should explore it as it is, without imposing expectations, and keep an open mind about how it operates. Currently, there's a hypothesis that attempts to explain why gravity is so weak compared to the other fundamental forces. It suggests that gravity may be diluted into additional dimensions beyond the ones we can perceive. These extra dimensions, proposed by theories like string theory, would allow gravity to spread out over a much larger area, making it seem much weaker in our 3D space. Imagine that gravity is not confined to the familiar three-dimensional world we experience, but instead extends into these hidden, extra dimensions. As a result, gravity's strength is diminished in our visible universe, while it continues to be concentrated in the unseen realms. This would also explain why gravity appears so weak at the scale of everyday objects. It's being spread thin. However, if we take these dimensions into account, it could allow gravity to be just as powerful as the other forces in certain contexts. Unraveling the mystery of gravity is critical for understanding the structure and future of the universe. Unlike electromagnetism, which operates primarily at microscopic scales, gravity is the only force that governs the behavior of massive objects like stars, planets, and galaxies. It operates on a macroscopic scale, which means that it's the fundamental force that shapes the very fabric of the cosmos, influencing everything from the formation of galaxies to the ultimate fate of the universe. As such, gravity plays a key role in determining the geometry of spacetime itself, and how matter and energy interact on a cosmic scale. Through our study of gravity, we have uncovered even more profound mysteries, such as dark matter and dark energy, two elusive phenomena that are invisible to our eyes but believed to make up the majority of the universe's mass and energy. For a deeper dive into these fascinating topics, feel free to revisit the first and second episodes of this series. One of the most exciting implications of gravity's ability to curve spacetime is the possibility of bending the very fabric of the universe. However, as much as we dream about reaching distant stars, the speed of light acts as a significant barrier. The vast distances between stars and galaxies, when combined with the limits of our current technology, make interstellar travel seem impossible within human lifetimes. For example, reaching Alpha Centauri, the closest star system to our own, would take over 2,500 years using current technology. This limitation paints a grim picture for humanity's ability to explore the stars anytime soon. But that doesn't mean we've lost hope. In science fiction works like The Wandering Earth, we get a glimpse of the kind of technological advancements that could one day help humanity overcome these distances. In The Three-Body Problem, Liu Cixin imagines a radically different solution. In his universe, advanced civilizations have developed the ability to fold space using gravity, allowing them to travel across enormous interstellar distances with ease. If we could unlock the secrets of gravity and harness its power to manipulate spacetime, perhaps we could create technologies like wormholes, hypothetical shortcuts through spacetime that could drastically reduce travel time between distant parts of the universe. If such a feat were achievable, it could open the door to the colonization of the entire Milky Way, transforming humanity's place in the cosmos. So, as we continue our quest for knowledge, we must keep pushing the boundaries of what we know about gravity. Because if we can understand and control it, the potential for discovery and exploration is truly limitless. Alright, that wraps up our discussion on gravity for today. In the next video, we'll explore one of the most fundamental yet hardest concepts to grasp in the universe: time. It's something we all experience daily, but its true nature remains one of the biggest mysteries in physics. What exactly is time? How does it differ from space, which we can perceive more directly? Are they connected in ways we've yet to understand? Okay, see you next time on Cosmos Unclocked.